Welcome back, class, and welcome to the new unit. In this unit, it is going to go a lot quicker. We are not going to be able to get to everything due to time constraints and moving to online schooling and all of those good excuses. But up here in this unit, you're going to see all of the things that you should be able to do. We're not going to get to all of these things. Alright, so if you're freaking out wondering why you've never heard of any of these things, that's okay. As long as you understand what I'm going through in the notes, you're going to be okay continuing on in this course and as well as in Physics 30. So, on this new unit, we're going to first look at gravitational force. To begin gravitational force, we've already done some of this. Alright, we've talked about gravitational force in the terms of weight. So in these terms, we have the formula on our formula sheet. That is G is equal to the force due to gravity over the mass. When we did this before, we had the gravitational force or weight, which is the same. We had the mass, which is the same. But for G, we use this to represent the acceleration due to gravity. Now we call that the gravitational field strength in a lot of our situations. They are going to be the same number. So on Earth, it's the same constant. It's 9.81 meters per second squared. Or it's going to be 9.81 newtons kilograms. That's going to make more sense as we go through it. So the way you're going to use this formula most of the time is that the force due to gravity is equal to the mass times the acceleration due to gravity. So that was review. On this next page, we're going to get into something a little bit new to us, but hopefully it doesn't get too tricky. According to Newton, all objects in the universe are attracted to each other by a gravitational force, a force that attracts any two objects with a mass. So this was like before when we had talked about if Sally is standing on the Earth, Earth has a gravitational force pulling her down, but she also has the same force pulling the Earth up. Alright, we have the formula we can use now, which we call Newton's universal law of gravitation. This is represented by the force due to gravity is equal to the gravitational constant times mass 1 times mass 2 divided by r squared. So in this, we have Fg, which is the gravitational force or weight. That's nothing new. What these two lines on the side mean, that just means that you're going to find the absolute value, or your answer is always going to be positive. M1 is the mass of object 1, M2 is the mass of object 2. R, sometimes you'll hear it called the radius, but it's not the radius in the same way that you would look at a circle. It's the separation distance. It's how far the two masses are apart from each other. G is the universal gravitational constant. This is constant. This never ever changes. Alright? It's represented by the value of 6.67 times 10 to the negative 11 newton meters squared over kilograms squared. This here is not something you're going to have to memorize. This is on your formula sheet. Same with this formula here. This is also on your formula sheet. So if we talk more about G, or the universal gravitational constant, we can look at its units. How are they derived? So in our formula, we again have the force due to gravity is equal to the universal gravitational constant times mass 1 times mass 2 divided by the separation distance squared. So if I rearrange this, so I'm solving for the gravitational constant, I will get G is equal to Fg r squared over m1 m2. If I plug the units in for those values, we'll get Fg is newtons. The separation distance is measured in meters, and that's squared, divided by the mass in kilograms, and the second mass is also in kilograms. When we put that all together, it's Newton meters squared divided by kilograms squared. So again, our units for the gravitational constant are Newton meters squared divided by kilograms squared. Like I had talked about earlier, and what we have done before, is Newton's third law states that a force always exists in pairs. So if Earth exerts a gravitational force of 459 newtons on you, then you exert a gravitational force of 459 newtons on Earth. For every action, there's an equal and opposite reaction. It's equal in terms of its magnitude, opposite in terms of its direction. So if I draw the Earth here, and you're standing on the Earth, then on you, you're going to have the force of the Earth on you pulling down, which we can call gravity. So force of Earth on the person. And opposing that force, we are going to have the normal force acting up. Remember, this is what holds you there. This is what stops you from sinking into the Earth or floating up under the ground. So when we have Newton's third law, we would also have the Earth, and if we draw a free body diagram of what's acting on the Earth, we would have the force of the person on the Earth. Alright, so in the first case, the Earth is pulling the person down. In the second case, the person is pulling the Earth up. That's Newton's third law. What's going to happen though is this person, they are going to experience more acceleration because they have a smaller mass. So they have more acceleration. Or again, 9.81 meters per second squared, because they have a smaller mass. The Earth is going to experience less acceleration because it's got way more mass. Now this is not something you need to remember, but it's going to experience an acceleration of about 8.71 times 10 to the negative 23 meters per second squared. It's got way less acceleration. It's a way smaller number. That's why the Earth doesn't go flying up to people when they jump off the ground. Okay, let's use what we learned to solve an example. In this example, we have student A has a mass of 75 kilograms. Student B has a mass of 50 kilograms. The distance between the two students is 4 meters, and we need to determine the gravitational force of student A on student B and the gravitational force of student B on student A. It also wants us to include a free body diagram showing the action-reaction pair. Again, remember, an action-reaction pair is what we use in Newton's third law. So if we draw this free body diagram, we have student A over there, and we can have student B over there. Now we know that student B is going to have a gravitational force pulling on student A. So this is the force of B on A. Similarly, we're going to have student A pulling on student B. Alright, so that's going to be the force of A on B. That's their gravitational force. Even though it might be really small, B still attracts A to it, and A still attracts B to it. They are separated by a distance of 4 meters. And now we have all of our information to start solving this problem. So first, let's look at the force due to gravity of A on B. So that'd be here. That'd be pulling B towards A. In that, we have our formula, which is G m1 m2 over r squared. Remember, this G is on your formula sheet. That is a constant that's always going to stay the same. So there we have 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared times the mass of A, which is 75 kilograms, times the mass of B, 50 kilograms, .0 kilograms, and that's all divided by the distance between squared, or 4.00 meters squared. So when you plug that in and solve, you're going to find that the force of gravity of A on B is going to be 1.56 times 10 to the negative 8 newtons. This seems a little goofy because from what we've done now, we always use the force due to gravity of the Earth pulling the object straight down. But now we're not worried about the force due to gravity of the Earth. We're worried about the force due to gravity of two different bodies. So in our free body diagram, it might be pulling to the left, might be pulling to the right, it might be pulling down, but it's important we draw it out properly so we know which direction things are going. So that's only the first half of the question. The other half wants us to find the force due to gravity of B on A. So to do that, we're again going to have the same formula. We have the force due to gravity of B on A is equal to G m1 m2 divided by r squared. So we have all that information. Again, this G is the gravitational constant, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Again, this is on your formula sheet. You may need to look it up there, but I'm guessing you're going to have it memorized by the end of these notes. Times the mass 1. In this case, mass 1 is going to be student B, because that's what's being pulled. Alright, it's being pulled towards student 1, so it's 50 kilograms, times mass 2, which is student A, 75 kilograms, divided by the distance between squared. Again, when you plug that in, you're going to get an answer of 1.56 times 10 to the negative 8 newtons. That makes sense that these two answers are the same, so these two lines should be the same. The reason it makes sense is because it's an action-reaction pair. Alright, they're going to be pulling each other in the opposite direction, but they're going to be pulling with the same magnitude. Alright, there's the same force being pulled, just in opposite directions.